So this coin problem is an oldie but a goodie. So the statement is that we have these 100 coins lined up, which I've drawn at the top here. They're numbered from 1 to 100, and they all start heads up. So I've drawn little H's above each of them for heads. And we also have 100 stick figures standing next to the table, numbered 1, 2, 3, up to 100. And these people are going to walk by the table and flip some of the coins. So for instance, person 1 flips every one coin, which means he flips all of the coins. So coin 1 is initially heads, this guy walks by and he flips it from heads to tails. So that one flips, coin 2 again flips heads to tails, and so forth. So all of them flip to tails after person 1 walks by. Now person 2, he's number 2, so he'll flip every 2 coins, which means he doesn't flip coin 1, but coin 2 he flips from tails to heads. So this one flips. And then coin 3 does not flip, coin 4 he flips from tails to heads, and so forth. Coin 6 he flips, and coin 8 he flips, and so on. So all of those are, all the even coins are going to flip on on person number 2. And now person 3 is going to flip every 3 coins. So you can see coin 3 flips from tails to heads when person 3 walks by. Coin 6 flips from heads back to tails on person 3, and so forth. So basically, person 4 is going to flip every 4th coin, person 5 flips every 5th coin, and then we get to person 100, and he'll only flip coin number 100. And the question we want to ask is, at the end of the day, after all 100 people have gone by, which coins are heads up and which coins are tails up, right? So this is very hard to think about immediately because there's quite a lot going on. So let's try to think about just some of the easier cases, the small numbered coins, and see if we can work those out explicitly. So let's see, what happens to coin 1, right? Well, coin 1, since all of them start heads up, coin 1 will start heads. The only person that flips coin 1 is person 1, because person 1 flips every coin, but all of the other people will flip either only the second coin, only the third coin. They all skip the first one. So that means this thing only flips once, and coin 1 ends on tails. Okay, what about coin 2? Well, now person 1 flips coin 2, and person 2 flips coin 2, so this guy flips twice. He flips on person 1, because 1 flips every coin, and on person 2, because 2 flips every other coin. So it started heads, flips twice, which means it went back to heads. So this guy ends heads. Now 3 is similar. 3 will not flip on person 2, because 2 flips every other coin, but he flips on 1, because person 1 flips all the coins, and he flips on 3, because person 3 flips every third coin. So that means this guy will also end heads up. And then, well, I'll stop at 4, and then we'll try to figure out the rest of the pattern. So 4, well, here's where it gets interesting, because this guy flips on person 1, because 1 flips all of them, 2, because 2 flips every other coin, and 4, because 4 flips every 4th coin. So this guy flips 3 times, and he's going to end on tails. So how can we figure out whether a given coin, pick a number, whether that given coin is going to end on heads or tails? Well, maybe you can see the pattern here that each numbered coin, say 4, is going to flip on all of the people whose number divides 4, right? 1 is a divisor of 4, 2 divides 4 into 2, 4 divides 4 as well, so he flips 3 times. So for instance, if we wanted to figure out some random coin, I'm running out of room here, but let's go down here. So to find whether a coin is heads or tails, let's see, to find heads or tails, we want to count the divisors, right? Count divisors. So what do I mean? Let me just do one more example of counting divisors. So what about coin 10? What happens to coin 10? Well, coin 10, well, the divisors of 10, the numbers which, when 10 is divided by that number, you get an integer back. So all of the divisors of 10 are 1, 2, because 10 divided by 2 is 5, 5, and 10. So we count them. There's 1, 2, 3, 4 divisors, which means that coin 10 flips an even number of times, and an even number of times flipping means you get back to where you started. So he's going to end on heads. But let's think about a different one, coin 16. Well, which numbers divide 16? Well, 1 divides 16, 2, 4, 8, 16. Those are all the numbers that divide 16, and there's 1, 2, 3, 4, 5 of these. So this number has 5 divisors, and if you flip an odd number of times, you're going to end up tails. But this is pretty interesting because divisors normally come in pairs, right? A divisor is a number which divides the number we're talking about. So 10 has the divisors 1 because 10 divided by 1 is 10, but it also has the divisor 10 for the same reason, because 10 divided by 1 is 10. So you would expect that these divisors would usually come in pairs, right? So the divisor 1 is paired with the divisor 10, and the divisor 2 is paired with the divisor 5. So you would expect that most numbers have an even number of divisors and end up heads. How could a number have an odd number of divisors, like 16? Well, 16 is interesting because most of these divisors are paired. 1 is paired with 16, 2 is paired with 8, but this 4 is unpaired. So why does 16 have a divisor 4 that doesn't come with a partner? Well, to find the partner, you would normally take the number on the coin and divide it by that divisor. But 16 divided by 4 gives you 4 back. So in some sense, that divisor is repeated, because 4 times 4 equals 16, so the divisor 4 is kind of its own partner. And now we have an idea for the answer, because the only way a number could have a repeated divisor, which means you divide that number by some divisor and get that same divisor back. Maybe I should start writing things. So the only way, I'm just going to pick some letters for these divisors. The only way, say, some coin number C divided by divisor n. So this is like, for instance, C is 16 and n is 4. And you get the same divisor back, which means I'll put n on the right side. That's just the case that we're talking about here with 16. 16 divided by 4 gives you 5 or 4 back. The only way you can get that is if C is a square, right? So now we have a guess. Our guess is that all of the coins that end tails up are the perfect squares, because they are the numbers that have a repeated divisor. And if we look at the table, if we go back up here, some of the examples I did, well, which were the numbers that ended tails? Well, 1 ends tails, and 1 is a perfect square because it's 1 squared. 4 ends tails because it's 2 squared. The ones we did down here. 16 ends on tails because it's 4 squared. And in fact, I won't go through all of them, but you can check yourself, or maybe you're just convinced by the divisor argument. But this is in fact the answer, that all of the coins that are perfect squares end tails, and all of the others end heads. So we haven't really completely checked this, but I'll leave this to you and just tell you the punchline. So the punchline is that the perfect squares are going to end on tails. Perfect squares end tails up because they have this repeated divisor, and then all other coins will end on heads. So if you really wanted to answer the question as phrased, which asks you to list all of the ones that end on tails, I guess you just have to list all of the perfect squares between 1 and 100. So that's 1, 4, 9, 16, 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 100. So that was a kind of messy way of writing all these, but those are the numbers which will end tails up. Okay, so that's the answer to the problem. You might ask why this seems like a very complicated problem to ask, and I say yes. The hope is that in attempting this problem you would initially be frustrated and not know what to do. And you might ask, why are you being cruel and frustrating me? And the point is that this is the sort of problem that it's much closer in spirit to what working mathematicians do. The first time I saw a problem like this was in my freshman year, and I had been used to problems from math classes where it's more of a cookbook or a set of instructions, right? The teacher says, to complete the square, you do this and this, take b over 2, add this squared, try to complete blah, 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 and you follow the steps, and then you get the right answer. And I never liked this because it seemed that this wasn't testing whether you were good at math. It was testing whether you're good at following instructions, which is really testing whether you're obedient, right? Whether you can listen. But that's not what mathematicians do. What mathematicians do is look at some interesting pattern and try to figure it out, like we just did here. We defined this strange flipping system and then tried to figure out the pattern, and it wasn't clear what to do at the beginning, and we were confused and had to try some things and look for ideas, and there was no set of steps to follow. We just kind of had to think up ideas and see what worked and what didn't. And I found this, when I first saw problems like this, it was really appealing to me. It was like going from drinking watered-down coffee to espresso, or perhaps a better analogy is going from drinking watered-down coffee to doing crack cocaine, because I became very addicted to these math competition problems. So my hope is that possibly you will become addicted to these as well and start to realize that math has a sort of depth and beauty and a sense of exploration that's really quite exciting. Okay, so thank you for listening. That's all for now.